Hi, my name is Tay.
My name is Yang.
Our project name is MOE. It's the mixture of experts. So today I'll present our CSE 147 final project, GPU accelerated tennis match simulation with CUDA and MOE routing.
And the goal of this project is to speed up tennis match prediction using GPU parallelism. Our application takes two tennis players as input and loads their historical statistics from CSV files and runs a large number of Monte Carlo match simulations. The final output includes the predicted win probability for each player and the average total games, median total games, and over or under probabilities for a selected total games line.
So the original version of this project was mostly Python based. Python was used for loading data, resolving players' names, aggregating statistics, and generating plots. However, the actual simulation loop became slow when we increased the number of simulated matches. Since Monte Carlo simulation requires many repeated independent trials, this part is a good fit for CUDA acceleration.
So our main idea is simple. Instead of simulating matches one by one on the CPU, we assign many independent match simulations to GPU threads. Each CUDA thread simulates one complete match, including sets, games, and tie breaks. The thread then writes two results, the total number of games and whether player one won the match. Uh, each since each trial is independent, there is almost no need for communication between threads.
So the project pipeline has four main stages. First, Python resolves the player name and loads the CSV file. Second, Python aggregation player statistics into six main values. Uh, Dominant ratio, ace percentage, double fault percentage, first serve in percentage, first serve win percentage, and second win percentage is saved in a CSV file like this. So this is the dominant ratio, this is the ace, double fault, first in win, and the second serve in and win percentage. So each player has this type of files and save into CSV files.
And then the CUDA implementation is mainly in CUDA. It's mainly under CUDA mcsimulator.cu. The main kernel is called Simulate Matches. It uses a block size of 256 threads and a grid stride loop. This makes the kernel flexible because it can run different numbers of simulations without changing the code. If there are more simulations than active GPU threads, each thread simply processes more simulations using the stride.
For random numbers, we use CURAND, CUDA rand. Each thread initializes its own random state using the global thread ID, so different threads do not follow the same random sequence. This is important because Monte Carlo simulation depends on independent random trials.
We also implemented a mixture of experts, or MOE, router on the GPU. The router compares the two players using normalized feature differences. It has four expert models: a surface expert, a vertical expert, a head-to-head expert, and a form expert. The router uses soft top K routing, selects the strongest experts, and blends their outputs into a match-up strength value. And this value is then used by the simulator to adjust game and tieback probabilities.
So one design decision was to simulate one full match per thread instead of assigning each point or game to a separate thread. This makes the implementation much simpler and avoids synchronization inside a match. The trade-off is that there can be a warp divergence because different matches may finish after different numbers of game or sets. For this project, the trade-off is acceptable because we run a large number of independent simulations.
And now we'll show a short demo.
So this is Yannick Sinner versus Carlos Alcaraz, best of three. They were comparing with CPU versus GPU. So these are the result. We can see that the format is best of three, and then the probability of game going over is 15% and under is 30 game is 84%. It's guessing that Yannick Sinner has 56% win rate and Carlos Alcaraz has 43% win rate. It is approximately 127 times faster for best of three format. And then the CPU time is 227 millisecond and GPU time is only 1.7 millisecond. So for best of three, as we can see, it's about 100 times faster, and for best of five, it's about 200 times faster. And then this is the summary of Yannick Sinner versus Carlos Alcaraz test run.
Yeah.
As
Best of
we
three and best of five.
right. So as we can see, the results are very similar, about 100 times faster. And these are the graph. This is the win probability. This is the Monte Carlo simulation plot. And this the runtime comparison. CPU is about 200 times faster for best of five games. Okay.
And then we also faced several challenges. One challenge was choosing the correct parallelization unit. We chose one complete match per thread because it keeps the code clean, even though it introduced some divergence. Another challenge was probability calibration. If the MOE output is used directly, the probabilities can become too extreme. So we climb and shrink the value toward 0.5. A third challenge was connecting Python and CUDA cleanly, because the program needs to work as a user-facing command line tool, not only as a CUDA binary. There are also some limitations. The current simulator does not model every tennis-specific factor, such as injuries, exact surface contacts, or live match state. The current aggregation is also mostly done on the CPU after copying results back to the GPU. So in the future, we could add GPU reduction kernels to compute win counts, histograms, averages, and percentiles directly on the GPU. We could also extend the project to multiple GPUs because the simulation are independent and easy to partition.
So in conclusion, this project demonstrates how CUDA can accelerate a real Monte Carlo simulation workload. By moving the repeated simulation stage from Python and CPU code to CUDA, we achieve a large runtime improvement while keeping Python for data handling, command line usage, and visualization. These plots are made by Python. And that's all. Thank you.
Thank you.